Welcome to this third video on probability. In this question we're going to look at using tree diagrams, and I've got a number of examples of tree diagrams. The first one is typically what you might find on a foundation paper, and we're given some information here which I'll briefly go through. And it's us saying about a journey. Barry's journey home involves going through sets of traffic lights, some of which you might be on red, and in which case it gets stopped. The first set is saying probability of 0.4. The second set of traffic lights, you may be stopped or maybe on red, is 0.3. And then this statement here, these probabilities may be seen to be independent. We've come across this word independent before. What it actually means is that the two events are not related. It's like when you're throwing a dice. The first event is completely separate to the second event. There's no memory or connection between the two. So we can say from this that the traffic lights are working on their own, and in fact they're not kind of connected in any way. So what is the probability that Barry is stopped at only one set of lights? So this is typically, you've got this space here, you've got typically to fill this in with a tree diagram, and I've done this on the following page, which we'll have a look at. Okay, so here's my very rough sketch of a tree diagram. You're not marked for presentation on any of this, it's all about just the decisions. So, sorry, it's a bit scribbly. The first one, Barry is stopped at the first set of traffic lights from the question is 0.4. So the other branch of the tree means that he's not stopped at the traffic lights, and these probabilities need to add up to 1. So this must be, if we take 0.4 away from 1, we're left with 0.6. The second set of traffic lights, the probability here is different, so 0.3 that it's on red, and 0.7, again these two adding together, that it's on green, or he's not stopped at the traffic lights. Okay, and then if we look at the second branch of the tree, we've got here that he wasn't stopped at the first set, but of course he could be stopped at the second set. So again, probability is 0.3 for stopped, and not stopped 0.7. So we can look at the decision trees. Imagine first of all then, Barry sets off on his journey, he's stopped at both sets of lights, and I've just written SS to show that, stopped and stopped. The second option is that he's stopped at the first lights, but he's not stopped at the second set, so stop, not stopped. And then not stopped and stopped, and then not stopped at both sets. The question here is, what's the probability that Barry is stopped at only one set of lights? Well, there's two combinations here. In this one, he's stopped at the first set, but free to go at the second one. And in this one, he's free to go at the first one, but then stopped at the second one. So there's two instances where he could be stopped. These two, obviously, he's stopped at both, and he's not stopped at all. So we need to work out the probability. Now these are independent events, which means we need to multiply these two probabilities together and then add them together, because obviously there are two separate parts to this calculation. So in the first one, 0.4 times 0.7, that gives us 0.28, and 0.6 times 0.3, there we go, gives us 0.18. If we add the two together, the probability is 0.46. So he's just less than half the chance that he would get stopped. Okay, let's have a look at a slightly different question. This one, again, I've done here, but I'm going to just use some pens to illustrate this. So imagine here you've got the question saying there are 11 pens in the box. There's my 11 pens. 8 of them are black and 3 of them are red. I'll bring the 3 red ones to the front. 2 pens are taken out at random without replacement. Work out the probability the 2 pens are the same colour. So in the first exercise, we've got 11 pens, and the chances of picking a black pen are 8. There are 8 there out of a total of 11. And the probability of picking a red pen are 3 out of 11. So assume you pick a pen out at random, we'll pick a black one out. There are only 10 pens left. So the probability for the next branch of the tree changes from 11 to 10. So in this case, we do the first branch of this tree, there are, assuming you picked a black, as I did there are only 7 black out of a total of 10 pens. And we still have 3 red pens. Okay, looking at it the other way, assume I picked a red pen out, first of all, then I would only have 2 red pens to choose from for the second choice, but I'd still have my 8 black pens. So you can see that by just doing a little experiment like that just helps you visualise the problem. Okay, to the probability itself then, a little bit like the last question, these are independent events. My picking there's no memory of what pen I picked out. So in the first situation, we're using fractions here rather than decimals, we have 8 over 11 and 7 over 10 for if you were to pick 2 black. So these are black and black. So that's say two colours the same. And then the only other 2 that are the same colour are red and red. So red and red would be 3 over 11 and 2 over 10. So we need to multiply these 2 branches. So 8 over 11 times 7 over 10 gives us 56 over 110. And 3 over 11 times 2 over 10 gives us 6 over 110. And again, a bit like the traffic light problem previously, these are independent events. So because there are 2 options, 2 blacks, 2 reds, we add the probabilities together and that gives us 62 over 110. You could simplify this, but it's not asking you to do so, so you can just leave it like that. Okay, now we'll go on to another question. This question is similar to the one we just looked at, the bit here about without it being replaced. So in this question we have a bag which has got 12 counters, of which 6 are black, 4 are white and 2 are red. And a counter is picked at random without it being replaced, and then another counter is picked at random. So when you're doing these questions, it's very important to read the rules. Okay, again, we've done this question previously. You can see I've underlined without being replaced. So this one's a little bit more complicated than the previous question with the pens because there are 3 different colours in this one. So you can see the tree is a lot more involved. But these really do help you answer the questions correctly. So to illustrate that, we need to say 6 out of 12 are black, 4 out of 12 are white, and 2 out of 12 are red. For the second choice, because you've taken one of the counters away, there's only 11 to choose from. So you have to check these branches. If you picked up 1 black, you've got 1 less to choose from. So 6 over 12 there becomes 5 over 11 there. We haven't picked a white, so still 4 left. We haven't picked a red, there's still 2 left. Now considering the white tree, picking a white first would mean the white for the second pick has gone from 4 to 3. And obviously you picked 1 out already, so there's only 11 counters left. Same with the red, 2 out of 12 there. If you pick a red first, you've only got 1 red left to pick on the second choice. You'll notice as well, if you add these branches together, they all add up to 1. So, if you're looking at the question now, what's the probability that both counters are picked out of the same colour? So here we have 2 blacks, and we multiply the probabilities together to get that. 2 whites, so we've got 4 over 12, 3 and 11, gives us 12 over 132. And then we have 2 reds, we've got a red and a red, 1 over 12 and 1 over 11, gives us 2 over 132. So I've written other things in here which I'll come on to in a moment. So we're just analysing that one, and that one. 3 over 332, add together 12 over 132, and 2 over 132, gives us 44 over 132. So that's the probability for picking the same colour. Both counters are picked out of different colours. So this time we know what the probability is for picking a double colour. So we just need to take that away from 1. Remember, probabilities add up to 1. So rather than work them individual branches of each tree out, we just simply take 144 over 132 from 1, and that's 88 over 132. And then the last part is neither of the counters I've picked out are black. So we have to look at what are not black here. And again, if you work through this, the probability being is at 30 over 132. Okay, there are some more. I'll post this question out, but there are some more to have a look at here if you want to try doing similar example. My final one is, I've done this already, but I just want to explain this. This is from one of the AQA topic tests, and it talks about bias. This is another area in probability that crops up quite a lot. Sometimes probability we take as straight, there's no complications with it. In this case, we have a biased dice. So it's biased towards rolling on a 6, because normally probability on a dice is 1 over 6, and 1 over 5 is obviously higher, there's a higher chance of it landing on a 6 than would normally be the case. So the question poses that the dice is rolled twice, complete the tree diagram. Now I've obviously filled it in, but you can see here from the printed part of this was filled in. So again, each of these branches add up to 1/5 for it landing on a 6 must be 4/5 for it landing on any other number apart from being 6. And in the second row, the probability is still the same. There's no replacement here or anything with this one. 1 over 5, 4 over 5, 1 over 5, 4 over 5. So it's basically that branch repeated, but this just showing you the second row of the dice. The probability then of 2 6s are these two branches, a 6 and not a 6, not a 6 and a 6, and then 2 not 6. The question says, work out the probability of rolling exactly 1 6. So in this case, we don't want that one because that's both 6s, but there are 2 examples here. That one's got a 6 in it, that one's got a 6 in it, and then this one hasn't any 6s, so it's these 2. So we want to multiply these 2 probabilities together, these 2 together, and add them. And effectively, although the fractions are the opposite way around, you'll know from multiplying fractions that when you do that, we get the same result. So 1/5 times 4/5 is 4 over 25, and it's the same for the second branch. We just need to remember that these 2 rows are independent events, so they needed to be added together. So 4 over 25, add another 4 over 25, gives us 8 over 25. And if you want to, it doesn't give you any extra marks, but you can write that as a decimal if you wish. Okay, thank you for listening. And in the next session, we're going to have a look at Venn diagrams.